In this video, I'm going to make up an example coding project so we can experiment with the LCD that we've built in the last homework and the new functions that we just learned using the core timer. So you don't need to follow along with this, but you can if you want. And soon you'll be doing a homework assignment that's very similar. You'll be building a stopwatch. So we're not going to quite build a stopwatch, but we'll be doing pretty much everything you need to build a stopwatch here. So what do I want to do? For every project you ever do, you're going to have some specs. So here are the specs. I'm going to say if a button is pressed, I'm going to print to the computer something like enter a number. Then I will read it. So I'm going to scan the number that gets printed. Then I will print it to the LCD so I can see what the user typed in. Then I will turn on the LED. For this number of seconds, and then I'll turn off the LED. And then I'll loop. So I don't know why we would ever need something like this, allowing the user to set how long an LED will be on. But that's a nice little project to do. So let's first talk about the button part and the LED part. We're going to need to build circuits, and we could use the LED that's already on the NU32 and the user button that's already on the NU32. Let's build another circuit. Let's add those. So our LED, we have to choose a pin, and that will go to the LED, to a resistor, to ground. And we put the resistor in there so that when this pin turns to 3.3 volts, an LED that's on usually only needs 1.8 volts. So the rest of that voltage will go across the resistor. So we'll get something like 1.6 volts across the resistor, and then that will determine the current. A nice bright LED is like 1 to 5 milliamps. So typically we use like a 330 ohm, maybe down to 100 ohms or up to 1,000 ohms, but somewhere in that range is a nice amount of resistance to get a bright LED when this pin turns on. And when I look at my board, I want to choose a pin that's kind of convenient. So if I'm going to build a resistor, an LED and a resistor to ground, I don't really want to build it up here because then I have to jump a wire all the way down here or something. So I'm going to build down here. Let's choose, I don't know why. We'll do F3. Actually, the user LEDs are on F, so I'm going to do a different example. So let's do G3. So our pin will be pin G3. And then we need a button. So we have two ways to wire the button. We can do 3.3 to the resistor to the button to ground, or the button to the resistor to ground. That's usually how buttons are wired for some reason. And usually we have a 10K resistor. So when you push the button, this point is attached to 3.3 volts, and current goes through the resistor to ground, and the amount of current is very small because we are using a 10K resistor. When you're not pushing the button, no current is going to go anywhere. No current is going to come in or out of the pin. So there's no voltage across this resistor. So if one side is 0, the other side is 0. So this is called a pull down resistor. And the voltage when we're not pushing the button will be low. And when we push it, it will go high. Okay, so that's one way to do the button. The buttons on the NU32 are wired the other way, 3.3 volts. Pull up resistor to button to ground, and this would be high, and when you push the button it would go low. Let's build this one just to compare. First we'll find those components, build these circuits, and then we'll do some code. I'm going to get out my little baggie from the kit, and I need to find a 10K, and I drew a 330 here, but I didn't do 330s in the kit. Well, let's not do 330, let's do a 1K resistor. A 10K resistor is brown, black, orange. So here's the 10K resistor. And a 1K resistor is brown, black, red. Here's my 1K resistor. Get those out of the way. And then my other baggie, find some LEDs and my button. So these comically large resistors, those are power resistors. We'll use those later when we calibrate our motor. I'll choose a red LED. We also have green, yellow, and super bright. Put all those away. And finally, here's a button. And this particular brand of button, all the buttons, they come embedded in this long piece of tape. So I cut them up individually and gave you one. They're held in the tape because their legs have little flat spots. You can kind of see them here. Those don't fit well in the breadboard. So don't pull your button out of the tape. Instead, cut it out so you have the round wire legs. If you pull it out and you get those little square ends, they don't fit well in the breadboard. So we'll chuck that. And let's build this circuit. So I said pin G3 will be LED resistor ground. I'm just going to take my LED. The long side of the LED is positive, so that'll go in G3. And then the other leg has to go in a row in the breadboard that isn't used for anything else. So I don't want to put that in a row of another pin of the PIC because we don't know if that pin's been told to be an output or something strange, and it'll interfere with our circuit. Okay, and then I'll use my 1K resistor to go from the LED to ground. And I should define what pin I want to use for my button circuit. So that would be this voltage here, the junction between the push button and the resistor. Let's have that be, I don't know, we'll do F5. F5. So F5 is down at the corner. So I need to, I'm going to have my button. It's going to start at 3.3 volts, and then the resistor will bring it to ground. So I need a little wire that connects the button to 3.3 volts. So I'm going to use my wire strippers to cut just a little piece of wire, strip both ends. Okay, now my button has 3.3 volts. And then I need a wire that takes that, the junction between the resistor and the button up to 5. Now, it's usually not very safe to build circuits like this while the power is on, but these are so simple that I'm not too worried about shorting anything. Cross your fingers. Okay, so I have these two circuits. I haven't been able to test them, right? I could get out my multimeter and I could look at this voltage relative to ground and verify that when I push the button, it goes to 3.3 volts when I push the button and ground when I let go. I can also take my LED and I could put one leg in 3.3 volts to see that it turns on. Not sure if you could tell. That's on right now. Let's go back to G3. And that's off. So we'll see. Maybe 100 ohms is better there to be extra bright so the camera can see it. But I could see it when that was on. And I still got my LCD all set up. So great, we've got our circuit done. Now we've got this, spec for how this code should work. So if the button is pushed, we're going to print to the computer using the NU32 UART3 print command, enter a number. Then we're going to scan that number and we'll print it to the LCD so we can see it. And then we'll turn on the LED for that number of seconds, turn it off. So we'll use the core timer to determine the amount of time. We need the NU32 read and write functions, and we need the LCD write function. And all of those require the NU32.h file to get access to the SFRs. And we need the LCD functions and C&H file so that we can make the LCD work. So let's swing over to our file system. And the first thing we always do is we're going to copy our skeleton folder. And I'm going to rename this, I don't know, I'm going to call this button, for lack of a better name for what this project should be. And then I know I need the LCD stuff, so I'm going to take my LCD.c and h and put them in here. I don't need LCD write.c. Although we could take that. How about we do that? We'll base all of this code off of the sample code. So I'm going to copy all of those into my button folder. And I'm just going to rename this main C file button to match my project folder name. So let's take a look at the code in Visual Studio Code. So I made this new folder called button, and we've got our button.c, and I don't know what else we really need to look at here. Our make file's already done. It knows the name of our port. It knows the location of our compiler. lcd.cnh are already done. NE32.cnh are already done. So all we have to really do is modify this piece of sample code so that we do the little assignment I've given myself. So I'm going to go through these. I'll simplify by deleting some comments because I already know what these do. So we've got NE32.h and LCD.h. I don't know why it's saying it can't find these. Visual Studio Code isn't the compiler, so it doesn't really even know where to look for any of this stuff, but we'll ignore that. I think what it's saying is it can't find xc.h, which is included inside of NE32.h. It'll know when it does the compilation process. Okay, I'm not going to use a pound define in here. We'll get rid of that. And we're going to get rid of the initial variables because we're just trying to start with the bare minimum we need. In all of our NE32 code, we always start with NE32 startup. That should be the first line of all of our code. And since we have the LCD plugged in, let's do LCD setup. What else do we need here? We're going to want a variable that represents the number of seconds. So I'm going to call that in seconds. And maybe I'll initialize it to 0. So eventually the user will give us the number of seconds. We need to be able to scan in the number initially as a character array. So we'll call that message, or just mess. And I don't know, I'll give it possibly 15 characters. But they're going to be typing in a single number, so should never really be typing in 15 letters. So the thing that they type in will get put into message, and then I will scanf it out of there and put it into seconds. And okay, let's go from there. So we have a button on pin F5 and an LED on pin, should I say, G3. So we need to deal with the button first. Let's say that we have to make sure that this pin is an input pin. That's tris, so tris f bits dot tris f5 equals 1. So that's how we make F5 is an input pin. Okay, now let's make the LED pin an output pin. So that's going to be tris g bits dot tris g3 equals an output. So G3 is output. And then I don't know whether when I make G3 an output, is it going to turn on or off at that moment? So let's just say let's turn it on. Tris this is lat commands whether it's on or off. Lat g bits dot lat G3 equals 1. So the LED is on. And the rest of this code came from our LCD example, so I'm going to comment it out. We don't need it right now. And before I go on, I should test this code. I should make sure that my LED turns on and everything compiles right. What else could I possibly want to do? Maybe I should clear the LCD so it starts blank. Okay, so these are all of our kind of initializations. Save that. And we're going to move over to our terminal. And I need to cd into this location. Button. And I just make sure everything's there. And then I'm on Windows, I'll use min-gw32-make. Everybody else is probably using make. And while I'm doing that, I'm going to put my pick in bootloader mode. So I'm going to do reset user, and verify that LED 1 on the pick is blinking. My computer's just awfully slow at compiling this. Okay, here we go. I think because I'm doing the video capture, it makes it run extra slow. Okay, the pick is in bootloader mode. So now that's compiled and it didn't have any errors, I could say make write. Pick is now programmed. And when I go and look at my board, oh no, my LED's not on. He's not plugged in all the way. I'll show you that real fast. So my LCD is blank. My LED is off. I can usually, so when I did the bootloading process and I loaded the code onto here, the LED stopped blinking, but I don't really know if my code started running yet. It doesn't always kick over. So I'm gonna hit the reset button just to make sure whatever code is on there is started over again. My LED is still off. Let me just make sure I'm in pin G3. Let's look at that code. Those are all the G's. So what I'm looking at is G3 is an output using tris, and then lat G3 is 1, so the LED should be on. That's always embarrassing. I'm gonna switch my LED back over to power to verify. Yep, it should be turning on. I'll put it back into G3. I don't think G3 is a special pin in any way, but we should probably verify that. So let me go open up. I'll take a look at the textbook, but we could also look at the data sheet for the pick. To just verify that pin G3 isn't some kind of special pin. Well, my computer will think about opening Adobe. Go. Add that to video capture. And now, okay. So what we're looking for now is the picture of the pick. Then we'll find pin G3 to see if there's anything about G3 that would prevent it from being able to be used as an LED. It's probably in chapter 2. And we have 2 versions of this picture. Here's the raw pick itself, and then we should also check whether the NU32 is doing something with G3. Okay, this looks like a lot of D's and E pins. E, D, F, E, E. Here's G678. Did I do that wrong? Did G even exist? Oh, here we go. Okay, so G3, that's a special pin. D plus and D minus, those are USB pins. I'm gonna have to double check whether we're allowed to, we'll probably have to turn off the USB module to be able to use G2 and G3. Okay, that was bad. Let's switch over to D8. That's just a little bit above D3. Okay, so we'll go back to our code, and we're going to be changing our G bits to D8. And we'll save that. And let's go rebuild. So if I want to, I can first do a make, just plain up make, be sure that my code compiles and isn't, I didn't like make some kind of big error. If I think it's going to work, I go straight to make right because it will compile and then try to upload it. I'll put my pick in bootloader mode and I'll try to do a make right. And we'll see if it compiles and uploads. Nope. So I must have typed something in wrong. Yep, just D, no 8 in this bits. I'll go make that change real fast. And pick's still in bootloader mode, so I'll try make right again. If we get lucky. Good. Ooh, and a wire from my LCD fell out. Figure that out later. Okay. So, back to the real world. My LED is on. That was hard. And I've got my button still hooked into F5. So hopefully F5 is a good pin for buttons. Let's move on writing code. Code is... Okay, so I need to wait until the button is pushed. So how do I do that? I could have an if statement. I could say if the button is pushed. So how do I know if the button is pushed? Well, I'm reading the voltage from F5, and that special function register is called port. So port F bits dot, I don't know why it's not port F5, but it's RF5 is the name of the bit that represents whether this pin is high or low. The button is low when it's not being pushed and high when it is pushed. So if I said if the button is pushed, now I know my button is pushed, and I would like to write something to my computer screen, so I'm just going to steal this from our sample code. If the button is pushed, I will say I need to enter an integer. And I don't want to go too much further than that before testing my code. So we will go back to the terminal, and I will put my pick in bootloader mode. And we'll try to make right. So now my LED should be on, and if I push the button, it's going to print a lot of times enter a number. So I can test that by doing a make putty. Because I'm on Windows. If you're on Linux or Mac, it's make screen. Try to show you what this looks like. I know the text is really small. So in the top left there is a window, and nothing's happened yet. It hasn't printed anything. So I'm going to push my button. Of course, I'm pushing the button and nothing's happening. Come on, F5. Did I not do the right pin? For fbits.rf5. Oh, just I'm not getting lucky. Ooh, that's fun. So I unplugged the button, the wire from the button. Yeah, I'll switch over and try to show you that. So in this scenario, when I push the button, nothing seems to happen. But you know what? I think just the wire was loose because now it's go. So here's my terminal screen and putty, and when I push the button, well, it just prints really, really fast because the code is probably checking that button a million times a second. And so when it does see that the button is pushed, it prints that to the screen, and then it reads the button again, and the button's still being pushed because my fat finger is so slow it can't get off the button fast enough. So it prints really fast. In the future, we'll be figuring out how to not have it do that. But for now, that was my test that I'm going to say it worked. So let's go back to our code, keep writing some code. Okay, so now I want to do NU32 read UART3. I want to read into my character array mess, and I left it 15 spots. And then I want to do a scanf from my function mess. I was expecting a single integer, and I want to put it into the address for all my number seconds. And also we noticed that I didn't put a /r/n at the end of my text there, so I want the this cursor to move to the next line after it's printed. We'll add that in. And now after I got that number, I want to print it to my LCD screen. So I'll move the cursor of the LCD screen to the top left, and then I'm going to sprintf into the same message again, might as well reuse it. I'll say s equals %d, representing the seconds, and seconds. Okay, so I push the button. It prints to the computer, enter a number. It waits forever until I enter a number, hit enter. I'm not going to do any error checking to make sure I didn't enter things that weren't allowed, so I hope the user enters a single number. I'll move the cursor to 0, and I'll print that number to the LCD. And then it will do it again every time we run. So put the book in bootloader mode. Now, very soon I'm going to figure out where that wire fell out. I've still got PuTTY open, so I'm going to close PuTTY because I can't bootload while PuTTY is open. The port can only be opened by one program at a time. So we go back over to the terminal window. Let's do a make rate. We got some warnings here. I used scanf and fprintf without doing a pound include stdio. But that's just a warning. So everything still works. My code is now running. So I'm going to do a make PuTTY. Get my terminal back open again. Show you what the terminal looks like. Okay, so when I push the button, it should print once to the computer, and that's really tiny. You might be able to see that. It says enter an integer. I'm going to type 4 and then push enter. Nothing happens on the terminal because I didn't tell it to print anything back. And now there should be a 4 on my LCD, but I let a wire fall out of my LCD. So let's figure out what wire fell out. Something on the right side of my board. I have to go back to chapter 4, of course, in the textbook. Figure out what pin that was. Okay, it should be, let's see, it could be D4, D5, or B15. So it looks like it was D4 fell out. Okay, the LCD is still blank because even though I fixed the communication here, the event that told it to print something here already happened, so it missed it. So I'm gonna hit the reset button on my pick so that we start over, and we'll go back to PuTTY, and I'll push my button. It'll say enter an integer. I'm gonna type 4 and hit enter. Of course, I did not get the number 4 show up on the LCD. Looks like all the wires are hooked in right. Power in the ground, everything's in. Wow, just not doing a good job here. Making sure my code is debugged. Let's go back and look at the code and see why the LCD is not printing. So we start up the NU32, we start up the LCD. That's the same as our previous piece of code. Hold on, the dog's eating something. Barcy, don't eat that. Come here. Hey, get out of here. Dog. Okay. Eat that, I see you. He's bad. Oh, and so of course nothing's going to show up on the screen. I told it to move the cursor and I sprintf'd in the mess, but I never told it to print to the LCD. Okay, so now we're going to copy our line that says print to the LCD. Hopefully you're following along and you're watching that being like, wow, he never did that. Yeah, we save that, we close putty, put the pick in bootloading mode. We will skip showing you putty and just go straight to the LCD. Go run right. We yell at the dog again. Hey, stop beating my camera. Hey, Barcy, come here. Barcy. What a bad dog. Okay, programming. I'm going to do putty. And let's see, can you see my screen? And so in putty, I push the button. It says print an integer. I take the number 4 and hit enter. And I got s equals 4. Yay. So this is pretty torturous. Okay, I'm going to close putty. And I'll go back to our code. So now we've got one more thing. I now want to turn on the LED for that number of seconds. Yeah, see, when you bite the camera, it falls on you. Sorry, that was the dog again. Okay, so I left my LED on, but I probably want the LED to be off to begin with. So let's turn the LED off. Lat d bits dot lat d8 equals 0. So the LED was on. We initialized the LCD. Now the LED is always off. Here we will turn the LED back on again. Lat d bits dot lat d8. LED is on. Now we need to wait seconds. Come back and fix that in a second, and then we'll turn the LED off. In fact, we can even skip turning the LED off because we know at the top of the loop it does it for us. So that will always turn the LED back off. So all we have to do here is figure out how do we wait that number of seconds. Well, we saw that we have a function for setting and reading the core timer. So let's use that. So we'll say, what is it? It's CP0. Set count, of course. So we're going to set that internal 32-bit unsigned number to 0. And then we want to essentially, we'll do nothing while we wait for that to hit seconds. So we'll say while, let's read the value, CP0 get count is less than, let's see, if we said 40 million, that would be exactly 1 second. And so inside that while loop, we're not going to do anything. We're just going to come back and read get count again and again and again. So 40 million ticks, because we're running it, the core timer counts at half the speed of the system clock, which is 80 megahertz. That's 1 second. So if I said that times s, or seconds, that would be the number of seconds to wait. Our only fear is that this number is bigger than the maximum value that it's allowed to be, which is an unsigned 32-bit number. Or really, seconds is probably a signed number, because I didn't specifically say seconds should be a signed number. But so that means its largest possible value is like 2 billion. So this number has to be less than 2 billion, or otherwise weird stuff is going to happen. We'll just assume the seconds is always going to be pretty small. We won't worry about doing error checking. Okay, we'll save that. Go back to pick, but I'm going to, in the background, do right. I'm going to put my pick in bootloader mode. He's blinking. Still compiling. Still compiling. Okay, it's programming. Now the code is running. We see that the code is running because the first thing it does is it clears the LCD screen. Now it's waiting for me to open putty. So I'll go into putty. I'll push my button. My putty says enter a number. I will say 4. Double check that you can see what's about to happen. So up here is my LED. So we're going to see S equals 4, and then hopefully the LED stays on for 4 seconds. enter. And I'll push the button again, and it printed enter an integer on putty, and this time I'll say 2 and enter. 1, 2, off. And I'll do it one more time. Say 1 second, enter 1. Okay, so that was my silly coding assignment. I hit just about every possible bug there was. So hopefully that was informative watching me struggle. But some key takeaways you can do from here. Always start with code that you kind of know works. So we're starting with this LCD example and just commenting out the stuff we don't need and building stuff as we go. Don't ever write more than a few lines of code without testing, because I never would have caught all of those bugs if I'd written the whole thing and then run it. They're just all the bugs would have compounded each other. I couldn't figure out which is which. So it was good that I only ran a couple at a time. And then remember that these print functions, those are very helpful for debugging. So I could add more print statements as I go to make sure my code is hitting certain steps of the process. Also, just turning on LEDs, that's a good way to debug. I can turn on an LED to know whether it got there. And now that you've got your LCD hooked up, and as long as you think the LCD is working, you could also debug print things to the LCD.